Today we're going to take a look at the bungee problem. The bungee problem is a classic energy type problem that we see in physics, where we have a bungee jumper and he's on some sort of bridge or support and he jumps off. He's attached to a bungee cord, which we're going to assume acts like a spring, which behaves according to Hooke's law. And he starts out with a lot of gravitational potential energy and falls, and then in the end ends up with a lot of elastic potential energy at the bottom. So the first question is, can we figure out, given the mass of the bungee jumper, the spring constant K of the bungee cord, the rest length L of the bungee cord, so there's some rest length L here, rest length L of the bungee cord, if we can figure out the total distance that our bungee jumper falls before coming to a stop, we're going to call that h in this case, because this little h will be referred to the distance fallen, but at the same time it's also the height difference in the gravitational potential energy. So when we think about the energy situation, if we call the original A and we call the position A and the full stretch position D, the question is, how do these energies relate? Well, what do we know? We know the energy at A has to be equal to the energy at D. This ignores any air resistance that might generate some friction or heat lost to the surroundings, or any stretching or any heat that would be generated during the stretching. This is the easiest way to solve this problem. So what do we know here? At A, there's no kinetic energy because he's not moving, and there's no elastic potential energy because the spring hasn't started to stretch yet. And so we're left with here all gravitational potential energy. And at D, again, he's come to a stop here at its maximum stretch distance, so there's no kinetic. We're going to call this bottom here h equals 0, because if it's h equals 0, then there's no gravitational potential energy. And so we're left with all elastic potential energy. Working these out, once we have these, we can plug and chug. mgh is equal to 1/2 kx squared. These are the general forms for those two. Now the problem is that if we know the mass and the spring constant, we know the gravitational field strength on the Earth is 10 newtons per kilogram. How does h relate to x? And it turns out that if you look at the diagram the way we've drawn it up, L is the rest length. That's how far he falls before it starts to stretch. And then we have this is our x. That's our stretch distance. That's how far it stretches. And we notice that L plus x has to be equal to my h. So L plus x is equal to my h. And now if you substitute this in, so the question is, do we want to solve for h or do we want to solve for x and then find h? Because we're looking for h is the question. So when I rewrite this, I'm going to write x in terms of L. So x is equal to h minus L. And if I go to put this, substitute this back in here, I end up with this mgh is equal to 1/2 k, but here's my x here. I have h minus L squared. And so looking at this problem, we can see we're going to get some sort of quadratic here, because this is going to be an L squared, there's going to be an h squared term here, and you have an h term over here. And so if you expand this term, I have mgh on this side is equal to 1/2 k times the quantity h squared minus 2hl plus L squared. So now what we have here is we have an algebra problem where we have just one variable that we don't know. So if we're given L, the rest length of the bungee, we can plug that in. And so if you look at the problem, say, what do we know? Well, If we're given the L, we're given the spring constant, we know the gravitational field strength, and we know the mass. The only variable that we don't have here is the h, and you can simplify, and then you can solve. Once we have our maximum stretch here, we can go through and we can answer the next question. Okay? The next question says, what is the maximum acceleration of the bungee jumper? If I want to find the maximum acceleration of the bungee jumper, I have to consider where are the forces the most. And if I can figure out where the forces are the most, I can figure out where the acceleration is the most. We know that when the bungee jumper jumps off, as they're falling, they're free falling here until they get to the rest length. But after the rest length, the bungee cord starts to catch them. What ends up happening is the bungee cord starts to stretch, and the net force goes to 0. And then as they start stretching beneath that, the bungee cord starts pulling up on them more than the earth is pulling down. And so after a little bit of analysis, what we realize is that the maximum acceleration occurs at the maximum stretch. So the force diagram for that looks like this. We know the earth is pulling them down, we call that the weight, we label that with mg. And at the maximum stretch, this is the force by the bungee, we call it Fs for the force by the spring. We know that's equal to Kx, where K is the spring constant of our bungee cord and X is the stretch distance. Now, where are we going to get X from? Well, it turns out that we can get X from right here. In the last part of the problem, we solve for H, we knew L, and so you can get the X by doing the little subtraction. So if you knew how far they fell and they knew the rest length, you could figure out what the stretch was. And so we know from Newton's second law that the acceleration of an object is equal to the net unbalanced force over the mass. So in this case, the acceleration is equal to, how do we express the net force? Well, it's Kx minus mg all over m. So as long as we know the K is given, X we solved in part A, M and G are both given, here's the M again, we should be able to solve for A, no problem. The last part of this says, what is the maximum speed of the bungee jumper? What is the maximum speed of the bungee jumper? So the maximum speed of the bungee jumper, oftentimes we think that the maximum speed occurs when they've fallen until the bungee cord starts to stretch. A little closer analysis of this problem lets us know that maximum speed doesn't occur when the bungee cord starts to stretch. Maximum speed actually occurs at the equilibrium. So let's reset this problem. So we're going to go back and we're going to look at this problem and see if we can't figure out what's going on. So the bungee jumper falls the rest length L. The bungee jumper falls the rest length L and then stretches just enough to equilibrium. We're going to call this point C. So this point is C. We call this equilibrium. We call it equilibrium, but that's when the net force is equal to 0. So if the net force is equal to 0, what does that tell you about the forces up and down? Well, it tells me that at this moment in time, the mg must be balanced out by the force by the spring, which is Kx. And so we have balanced forces, net force is 0, acceleration is 0. So up until this moment, our bungee jumper has been speeding up. Even after the bungee cord starts to stretch, they continue to speed up until the force is balanced. Anything below this, and the spring force is going to be greater, so they're going to actually have acceleration in the up direction and start to slow down. So this is where their maximum speed occurs. So max speed occurs at equilibrium. Okay. max speed occurs at max equilibrium. So let's talk about that. What do we know then? The energy at A must be equal to the energy at point C. Here's our point C right here. As we talked about earlier, the energy at A is all gravitational potential. But what's going on here? Well, the easiest way to do this is to set h equals 0 here. So this is a new h equals 0, but you can set it anywhere you want. So this is going to allow us to say that there's no gravitational potential here, but our bungee jumper is moving, so there's kinetic energy, and our bungee cord has started to stretch some, so there is some elastic potential. So once we go, and then we're going to plug and chug this, so mgh is equal to, kinetic energy is 1/2 mv squared, which is good because we're looking for the max speed. That's going to be my v here, plus 1/2 kx squared, that's the stretch. So one of the things about this problem is, can we figure out what the h and x and L relationship is here? Much like the other problem, where we saw that L was the stretch distance, or L is the rest length, we still have some stretch distance here, x. But this one's interesting because we can get a value for x here. So this time, I know that my mg is equal to kx in terms of the forces because it's balanced. So x, so mg over k is equal to x. So x is something that we can solve for because we're given in the initial problem the mass, the gravitational field strength, and the spring constant, so you can solve for x directly. So in addition to this, I know, like before, the total fall distance, h, is equal to L plus x. If we know L and x, we can solve for k directly. And so what we end up doing here is we're going to look at this problem and see if we have everything we need. So I'm going to take this, substitute these in, move it up here. So I have mgh is equal to 1/2 mv squared, that's the kinetic energy, plus 1/2, this is k, and I have, if I substitute in for x, I have mg over k all squared. On the left side, I know what h is equal to, so I have mg L plus x is equal to 1/2 mv squared plus 1/2. With a little substitution here, we don't need to sub, we'll just leave it like it is. Mg over k all squared. And let's see if we can solve. So the thing we're looking for is the maximum speed. We have the mass, we have the gravitational field strength, we have the rest length. X we can get over here. And then we have the mass, we have the k, we have the m, and the g, and the k. So we have everything we need to solve except for the v, and then we can solve for v directly. And this will allow us to plug and chug and find the maximum speed which occurs at equilibrium. And that is the full bungee problem.